Okay. We're going to finish chapter 4, and the last two topics are tides and measuring time, which is talking about the sidereal day. So let's go ahead and wrap up the chapter 4 slides. Okay, so first tides. So reviewing ideas of gravity. At what point on Earth is the gravitational force from the moon the largest? And they show a not to scale version of the Earth, the moon, and the distance between them, but the orientations are what we care about, not the scale. And we have points A, B, C, and D. So A is right on the side of the planet. B and C are on the part that's facing us, and then D is on the other edge of the planet. So where would the gravitational force be the strongest? Hey, all right, you all think point A. Well, you're right. And of course, that was not meant to be a difficult question, although I, I could see rightfully hesitating because you're like, wait, is this a trick question? And it simply comes down to that the force of gravity is proportional, wrong symbol there, but is proportional to 1 over the distance squared. So we've got this notion that 1 over r, where r is the distance squared, is the key proportionality for gravity, at least when we care about distance. And we don't care about mass because in each case it would be the same two masses, but the distance changes and A is just closer. Okay. And it's not that much closer, but it's enough because we have a distance here that's about 60 times the radius of Earth. And we have a distance, of course, then the additional distance to the far side is just one more, or rather two more radii, because the diameter is twice the radius, but it's an additional two of the radius of Earth. So, difference between 60 and 62, but when you divide by that number and you square it, you would certainly get a significant difference, a measurable difference. Okay? So gravity is always an attractive force, and that's what's shown here in these arrows. Is we see that the arrows which represent force are always pointing from the Earth to the moon. So this is the gravitational pull from the moon. The moon is attracting things on Earth towards it. This gravitational pull is small compared to the gravitational pull of Earth itself, but we've already talked about that. We only care about the additional gravity caused by the moon. So, in other words, things on Earth are slightly um, lighter on this side of the planet. They're getting pulled towards the moon, and you would be slightly heavier on the other side of the planet because you're getting pulled into the ground. But as we'll see, that difference is not, or rather, that idea of being slightly lighter or heavier isn't what actually is causing the tides because it's tiny. You don't notice how much lighter you are if the moon is directly overhead. You can't jump higher. You don't feel yourself drifting off into the air because the gravitational pull of the moon is so strong. That would be an unsustainable and physically unrealistic system. It's a tiny change compared to the steady gravity caused by being right on the surface of Earth, which is already much more massive and you're much closer to. Okay, so here are the tides. All right, so far we've identified that gravity is involved, but not in the straightforward way of just tugging on things. Okay, so that's where what I want you to be thinking right now. Gravity is involved with tides, and we need to see how it is. And we'll start by considering that two tides that occur every day. And those two tides, two high tides that occur every day are shown right here. There's going to be one on the side of the Earth that is facing the moon, and another high tide on the side of the Earth that is furthest from the moon. So right away, the whole idea that it's just about gravitational tug doesn't match this picture because if it was just about gravitational tug, there should only be one high tide a day. And if anything, only one low tide a day, because maybe you'd imagine that on the far side of the planet, all the water has, been pulled away and there's just less water over here. Right. So you might imagine, like the blue being shorter than it is at the poles if this kind of not to scale blue perimeter around the planet represents the oceans. And so you can imagine maybe, like a undisturbed amount of water at the poles because it's not, it's kind of an average different distance from the moon, but then extra low tides on the far side of the planet, and then, more water because it's all gotten pulled towards the moon on the near side. All right. But that picture would require basically the Earth being at rest. So if the Earth and the Moon were just like this permanently, then over time, maybe something like that could develop. To not get overly technical about it, but that would could maybe even describe a system, which we will touch on when we talk about the comets and asteroids and dwarf planets of the solar system. And we talked about Pluto because Pluto's moon Charon are in an orbit where they orbit each other and they're tidally locked to each other, which means that the same side of Pluto always faces its moon Charon. So that would be like if this picture for the moon and Earth was staying fixed in that the moon was always above the same section of Earth. It never moved around the planet, or rather, the planet never spun underneath its orbit. And that's not at all how the Earth and the moon work, but there are two body systems like Pluto and its moon that do work that way. And although Pluto doesn't have liquid oceans and we don't have a comparison, over there, if there was something like that on Pluto, we might imagine, a buildup over time where everything ends up being on one side of that planet. And so there would just, be a noticeable asymmetry between one side and the other. But that's not what's happening. Everything's about motion here. Earth's spinning underneath the moon once a day. And so what does that mean then? How does spin and gravity, how do they combine? Okay, well, let's look at the spin. So here's Earth spinning underneath the moon. And as we talked about, the moon's orbit around Earth is, much slower than Earth's rotation around its own axis. So within, the period of 24 hours, it's almost like the moon remains motionless and the Earth spins underneath it. Though, of course, the moon would move a little bit, in this case, kind of out of the screen towards us as it does its 3D rotation. Okay. So we'll include the sun in just a moment, but I do want to quickly mention that the key idea here then is that if it's if the tides aren't as simple as just pulling on gravity, what we need to think about what they're doing is interrupting the motion of the oceans. So the whole planet is moving, and that movement does contribute to overall currents, both in the atmosphere and the ocean. You have these phenomena known as the Coriolis effects that vary from the poles up to the equator, and then actually change their direction and then vary again from the equator to the poles. And all these circulation effects, this overall movement of fluids throughout the Earth is happening because of an energy exchange between hot and cold. It's happening because of the rotation of the planet. That hot and cold energy exchange obviously is being driven heavily from the fact that one side of the planet is in sunlight, the other isn't. So there's always a cooling and a warming going on. And so all these effects keep motion happening. So we have all this naturally occurring circulation within our oceans. And so what the tug of, because it is a tug, but what the gravitational pull from the moon is doing is just interrupting that circulation. And wherever the changes are most directly um, perpendicular to the surface is where that interruption is most pronounced. So just to go back to the forces, the reason that there's a high tide on these two sides, and say not on the two sides where where the moon is not, where the direction to the moon is parallel to the surface rather than perpendicular, is because the gravitational pulls on, say, the side that's right on the front, and the one on the back of the Earth, so the side of the Earth facing us and the side facing away from us in terms of the screen, the gravitational directions there would, as I said, would be parallel to the ground because they point sort of, it's like skimming across the ground. And almost, and if you think about right at the equator, right, they just point right along the equator, either due west or due east. And okay, so then those aren't going to interrupt flow very much. If anything, they're to contribute to the flow of water. But where the pull is perpendicular, either sort of pulling the water up towards the atmosphere or pulling it down towards the ground, both of those create an interruption, a a subtle but with a sort of chain reaction, domino effect, a cascading series of interactions. You have this overall behavior where the tides are being caused because of that perturbation, that disruption in the movement. What's interesting is that all of that is obviously, as I mentioned at the very beginning, really complex because tides vary so much between coastline, topography, in terms of structures of bays and inlets. There are tides that are over 10 feet on a regular basis, other tides that are just 2 or 3 feet in terms of high tides. And those are on the same ocean, but just very different sections of the same ocean. So you have, that the system is obviously all about, all this moving fluid, and we're just setting a an overarching disruption to that system. Okay, I'm gonna make sure there was no comments in chat. So if that seemed like general, it was meant to be, because that's the way that I've found it's best to understand tides, is to focus on what's not happening and understand that it's just about a subtle disruption to the flow. Okay, now a less nuanced, a less subtle, a less complex notion, which might be a welcome reprieve, is how the sun contributes to tides. Okay. So this one is, you can think of it as being as straightforward as whether the sun is directly lined up with the moon and is contributing to those perpendicular forces, and perpendicular because perpendicular to the surface, which are the two force arrows shown here, or the sun is not parallel to the moon and its contribution to gravity is the exactly opposite the moon's. Okay. So here we have an influence of the sun and moon when they are aligned or parallel to each other. So the forces of gravity towards the moon match up with the direction of the forces of gravity towards the sun. Okay, that creates a higher tidal variation. So when the sun and the moon are in this type of orientation, the high tides are higher and the low tides are lower. We call these spring tides, not because they're in the spring, it's just the name given to them. And it happens when the sun's gravitational force increases the size of tides, and it requires alignment between the sun and the moon. So, what phase of the moon do spring tides correspond to? Okay. I've got a vote for first quarter, new, waxing gibbous. Denise, what zero? I haven't seen that. Oh, change it to one. New. All right. So I decided that. You did had a guess. All right. One's got the most votes so far. So it turns out that you're right. New moons would be a cause of spring tide. That's a phase of the moon where spring tides occur. Absolutely. Notice that full was not an option because that would be another case of spring tide. You'd have two correct answers in that case. Okay? So both new and full moons cause spring tides to occur, higher highs and lower lows. Uh, you know, waxing or waning gibbous would be the next best, but not quite as good because the alignment would not be as direct in that case. Okay. Okay. So I mentioned there's the case where the sun and the moon are not aligned, and that is this orientation shown here. Again, everything's not to scale. So now we have the moon in an orientation where it's not, doesn't make a direct line with the sun. Instead, the sun, the moon, and Earth make a triangle. So this is a, a misalignment, an unalignment between the sun, the moon, and Earth. And in this case, because now the sun is, contributing the effects that we described, and it's doing it to the sides of the planet where low tide should be occurring. Well, now it's sort of, disturbing that natural circulation of the oceans in a way where it's causing a basically like a slowing, a retardation of that circulation. And in doing so, right, it creates a bit of a almost like a mini high tide where there should be a low tide, which means that there's going to be a weaker low tide. It's not going to be as low. And then it causes the high tides to not be as high as they would be when everything's aligned. So in this case, we refer to the tides as neap tides because the sun's gravitational force decreases the size of the tides. It's working against the effects of the moon. And what phase would this correspond to? What would be the phase that matches neap tides? Okay, got a vote for three. Another vote for three. I one more, and I'll say that you understand it. Hey, all right. At that point, though, I'm sort of I said, just say three. Must be three. No, but I think you do all know. Indeed, it is the first quarter. The first quarter is exactly that orientation, which is a good review, actually, of the type of stuff we were talking about when we were just talking about phases, right?
Can you explain how you got three?
So it'd be by looking at this picture mostly, and by remembering that when the moon is in this orientation, the visibility of the moon from Earth's surface is that quarter, what we call the quarter moon, the first quarter
Oh,
or the
in
yeah,
relation to that picture, like that slide from last class where it had
yeah,
the different phases in relation
yep,
to this. Oh, okay.
exactly, yep, yeah. So it'd be a matter of comparing the two figures of the two pictures, yep, and then the other phase that causes neap tides is the third quarter. So there's always two phases that cause these types of tides, whether spring or neap, and they're always a half cycle apart, right? So new to full or first quarter to third quarter. And there's the last thing I wanted to add in here is that the actual gravitational pull from the sun is greater than the gravitational pull from the moon. And so that goes to show that it's the difference in the gravitational pull from one side or the other that matters more than the absolute strength. So it's the fact that there is a noticeable difference in gravitational pull from one side to the other that creates more dramatic tides than it just a than just a stronger pull. Because if you run the numbers, if you just plug into the universal gravitation formula, you plug in the mass of the sun, you plug in the distance to the sun, you get a value, the actual strength of gravitational pull on, just objects on the surface of Earth and that strength is greater than the strength that the moon exerts. But yet the moon is the dominating effect on tides because the difference of the gravitational pull from the moon from one side of the earth to the other is greater, proportionally greater, I should say. Okay, very last topic with chapter 4, measuring time. So if you recall, I briefly mentioned the difference between the month as we know it in terms of the phases and the month as an astronomer also knows it, which is the actual orbit of the moon around Earth, and how the orbit of the moon around Earth takes less time than the full cycle of phases, because the moon needs to orbit a little bit more to get back to the same orientation between Earth and the moon, because the Earth has moved through its own orbit in the time that the moon has been orbiting Earth. Well, that type of idea also applies to days itself. The very notion of how long it takes to get for a full day to go from, from sunrise to sunrise. What does that mean, right? What does it mean to have a full day? Well, you can start to think, well, I mean, the time, the length of the day changes because of the axial tilt throughout the year. So already there's, you can start to think, okay, well, sunrise to sunrise isn't an exact number because, it's going to be a slightly different time each day. And even if you accounted for that, you still have to think about the fact that Earth needs to turn a little bit more in order to face the sun each time because the Earth is going in that orbit, that elliptical orbit around the sun. But before we even get to that idea, let's think about the fact that everything about trying to quantify months, days, what numbers to choose is sort of a fraught endeavor because it's hard to exactly, there's no best choice. We're always going to end up with decimals. We're always going to end up with approximations because the values don't work out exactly. They weren't, it wasn't the we can, unlike the notions of the heavens that Ptolemy proposed back, almost 2000 years ago, where everything was about perfect circles and the assumption that the universe had to be made out of symmetry and alignment and perfection because no divine being, whether whether that be like Apollo or the god or whatever, could make the universe anything less than perfect. Why would they, right? Well, we know actually, whether or not any super powerful divine being was involved in the creation of the universe, it's a lot more messy than people thought it was 2000 years ago. Everything is about approximations and really complex systems that work in ways where they're difficult to quantify. And to drive home that idea, let's think about how how many days there are in the year, how many months fit into the year. So in a full orbit of Earth around the sun, if it took 360 days, an orbit of the moon around the Earth and an orbit of the moon around the Earth took 36 days, how many months would be in the year? Well, I think you can do the math. You would just have 10 months. And in a system like this, eh, you wouldn't have to make any approximations, right? You could just naturally split the year into 10 pieces. And the lunar cycles would exactly match those named calendar months. And there would just be 10 of them. If you had 270 days and the orbit of the moon around the Earth took 30 days, when 30 days being closer to our actual orbital period for our moon, you'd still have a nice division. You'd still have a case where the 30 evenly divided into 270, and it'll be exactly 9 months. But here on our planet, around our sun, things are not as exact. Our orbit takes 365.2422 days. Okay. And even that value can be written with more decimals. And there are a number of things that are, even slowly changing over hundreds of thousands of years. So, this is just the current value for Earth's orbit around the sun. The moon's orbit takes 29.5306 days. Now, they actually are referring to the moon's phase cycle that takes 29.5306 days because the slides don't touch on the difference between the orbital period and the period of phases. So calling it the orbit is strictly speaking not correct. They could say the moon's, cycle takes 29, the lunar cycle takes 29.5306 days. By the way, the actual value for the orbit is 27 days, 27 days for the moon to orbit Earth. All right. But if we just think about, just phases, right? So, they're going from new moon to new moon, then it's 29.53 days. Okay, well, the division can't be exact, right? 29.53 doesn't exactly divide into 365.24. By the way, the 0.24 is the reason that we have leap years because we have to account for that little extra time. Teresa, go ahead.
I just have a question regarding the moon orbiting around the Earth at 27, like you said, to
Yeah.
be I read 27.3. Is that
Yeah,
any
thank you. Yeah.
difference?
Yeah, yeah.
I didn't know any.
I
Uh,
couldn't remember the decimal, and I didn't just want to guess.
okay.
Yeah. So it's 27.3. Thank you.
I
Thank
just
you.
wanted to make sure. So if it ever comes up in a test or anything, we put the right answer in. I just wanted to make
Yep.
sure that it does matter. So 27.3, right? Thank
Yep.
you.
27.3. And do you remember the name for that type of say month or lunar period?
Are you asking me?
Yeah.
When I was reading it, said the moon orbits the Earth about every 27.3 days, but the time between observable lunar phases is about 29.5 days, not 2 days in an orbited moon as stated in the query. So what is
Yeah.
that?
As stated in the query.
Yeah.
I'm not sure. I'd have to look at the exact context of that statement. It must be referring to something else that they said earlier. But
Okay.
but also the they don't mention the term for the 27.3. I had mentioned it yesterday. It was called, although you're not responsible for the name, it was called the synodic month. And then the one that we know and the one that's mentioned here, the 29.5, is called the solar month.
On here, I just read it said the sidereal month.
Yeah, yes. Yep. So the sidereal, and then the solar. Yep. Yep. Yeah, so that one, that term is used as well, which actually is nice because it's the same as the sidereal day. So I think that I like that term is getting used because I always thought it was confusing to have two different names. So perfect. We got the sidereal month, which is shorter than the solar month.
Thank you.
Well, thank you, because it's the perfect segue to that idea that you are going to be responsible for on quizzes and tests, which is the sidereal day and the solar day. Okay. So, and oh, by the way, the sidereal month and the sidereal day, I think it might show up in a discussion question. So you could see it in a discussion question, but it wouldn't show up in multiple choice. But anyway, this idea, let's make sure we got the day down. Okay. So we've been talking about all these, you know, detailed differences between measuring time. Well, here there's even a question about what do we mean by a day? What is a day, right? Well, a sidereal day is what or how much time it takes for the planet to completely spin around. Just really, that's what it means. And the way it's often described is in a statement like this: an observer on Earth points the same direction in space. So in other words, if you have a sidereal day, and the figure does a good job of showing it, and you've got your little observer, which is this tall sort of silhouette shown in the figure in orange, they're pointing in a certain direction, and initially they are pointing straight to the sun, but you could also say they're pointing to some distant star, some constellation. And after the Earth makes a complete rotation, they're going to be pointing exactly in that same direction. So this solid white line that if you follow it past the sun, because it skirts just above the sun on day two, it says it points to a remote celestial sphere, to a point on the remote celestial sphere. So you could say it points to some distant star. So that is a full rotation because the Earth has turned all the way back around. And the reason we use a distant star as a reference point is because that distant star has remained fixed in location relative to us. So that's why it's a good reference to think about what rotation means. And if the Earth was literally like a spinning top, if you had a model of the Earth or even a globe and you spun it and you wanted to spin it at a certain rate, to match Earth's rotation, then it would be turning all the way around, and the time that took would be a sidereal day. Interestingly, that's not the day that we talk about most of the time. When we talk about a day, we do not mean a sidereal day. And a sidereal day does not have 24 hours. Instead, what people mean, including astronomers, when they refer to a day is a solar day. Because a solar day is the time it takes for an observer on Earth to point towards the sun again. And if we look at the figure, we can see that because the Earth has moved a little bit in its orbit around the sun from day one to day two, and it's moved, just a tiny portion of the overall orbit, which, takes about 365 days. So it's moved about a 365th of a day. Well, if we approximate that 365 to 360, then we have the number of degrees in a circle, and then we can say the extra angular rotation for the Earth to not just turn back to its same orientation, but turn so it faces the sun is 1 degree. So 1 extra degree of rotation is what the Earth needs to complete in order to finish a solar day. So a solar day is 1 degree longer, approximately, than a sidereal day. Right? Okay. So that's the difference between the solar day and the sidereal day. And as I said this many times, I meant not to give it away, but which day must be longer? The solar day. The solar day is longer. How many minutes longer is it? Anybody know? How many extra minutes in the solar day compared to the sidereal day? Yep, 4 minutes. Thank you, Maria. And then Max said 12.37. That's how many months would fit. Yeah. With the actual values. Yeah. So the solar day is 4 minutes longer than the sidereal day. And the solar day is exactly 24 hours, which means the sidereal day is 23 hours and 56 minutes. So that you can see that the solar day is chosen as the standard, and it's set at exactly 24 hours. So we choose and that's important because that means that the length of an hour is based off of the solar day. Therefore, the length of the minute and a second, they're all based off of the solar day. Although actually now there's a different standard for a second since the 1970s, but it was designed to sort of be consistent with that. But until the 1970s, that was the actual global standard of how a second was measured. Was exactly proportional to a solar day. Now it's based on how the time it takes light to travel a certain distance is like the official global standard. Not that it matters for many things, the tiny difference. All right. So yeah, yeah, I got an answer already to this question, which I was just gonna ask us if you could think about if the Earth rotated on its axis more rapidly, what would happen? Would one type of day go up and the other go down? Oh, I think I lost the slides there. Sorry. There you go. All right. Yep. So they would both be shorter, is what you're saying. Okay. Yeah, because the Earth would be spinning faster. You're saying that they both would be shorter. That's absolutely right. They'd both change because that rotation of the Earth would affect both of them. And interestingly, what if we orbited the sun faster? So that would be like this distance, this sort of like, distance along the blue line was greater in for one day. In other words, what if there was only, 270 days in a year, for example, but our orbit was the same? How would that affect these two values, the sidereal and the solar day? Okay, so we orbited the sun faster. It's just the one right here. If Earth orbited the sun faster, what would happen to the sidereal and the solar days? Okay, so I've been meaning to look into this one because I don't see how the sidereal day would change by definition if we orbited the sun faster. It shouldn't. I think this is a typo. So because the sidereal day would stay the same, but the solar day and the solar day would be longer. But that's not even an option they give. So I'll put a pin in this because I do agree that the solar day would be longer because we'd have to turn even more to realign with the sun. Because in other words, the extra angular turn to be pointing back to the sun would be, maybe 2 degrees, right? If there's fewer days in a year because we're going around the sun faster. The solar day would be longer. But the sidereal day only depends on Earth's rotation. It's independent of the orbit around the sun. So, because we're pointing back to the same point. Yeah. So I disagree with the answer, but I'll have, when that happens, I gotta make sure that, you know, there's a reason if I can find, a confirmation in a sense, or at least just, spend some time with it because I'm hesitant to just say it's a typo. But at the same time, I don't see how this sidereal day could change because of the orbital rate of Earth around the sun. Because the sidereal day just depends on how fast the Earth is turning, independent of the orbit. Anyway, things to consider. But the part I do definitely agree with is that the solar day would be longer. Teresa, what do you have to say?
Well, on that part, it says if Earth orbited the sun faster, our year would be shorter, and the apparent
Yes.
speed of the sun, moon, and stars across the sky would increase. So
Yeah.
how true is that? I mean,
I,
on
I,
this one, I hear that on the question that we were reading right now.
yeah, that's true that like, we go through the constellations faster, but on a given day, it would still take the same amount of time to come back around and be facing, the same direction in the celestial sphere.
Okay.
Yeah.
Okay, thank
Because
you.
I agree with what you said, but it doesn't. I still don't think that affects the sidereal day. It would just affect the sort of the length of like I said, going through the constellations, the how long you have to wait to see different stars in the sky and so on, or even the rate of change of seasons would be faster. All right, so then we can finally wrap that up. I don't have anything too much to say on
I
this
just
one.
want to be clear. The Earth orbiting the sun does not make our days shorter.
Um, if we orbited the sun faster, it would make our solar days longer. That's the part that I can say for sure, because I both me and the slides agree about that. So no, it would not make, and it wouldn't make anything shorter. It would make our solar days longer if we orbited the sun faster, which is kind of like counterintuitive, right? Because you're like, wait, doing something faster makes something else longer. But that's because if we were going faster around the sun, each solar day would mean that the Earth has to turn even more in order to face back in the correct direction towards the sun.
I'm so confused, but I'm going to keep listening.
Okay, so basically, just that I know I don't want to spend too much more time on it, but you see how it's 1 degree is the extra turn in order for the Earth to face back to the sun? Well, if the Earth moved even more, if it let's see, and I still I'm like, no, I don't think I'm sharing it. Okay. Doesn't help if you can't see it. So, yeah. So if I have, oh, it won't let me write it from zoomed in. But so if 1 day is way over here, so because the Earth is orbiting faster, okay, so now the Earth is over here. And so now day two isn't here, but instead it's here because of that faster orbit around the sun. Well, in order for a solar day to be finished, you have to have a point on Earth, in this case represented by the person standing on Earth. You have to have them pointing back towards the sun. So when the Earth was orbiting around the sun slower, that extra rotation for the person, the observer, to be facing the sun after 1 day was 1 degree. Well, what if that extra rotation was 2 degrees instead of 1 degree? Because we were moving twice as fast around the sun. Well, in that case, and this is day two, right? Not just coincidentally matching, 2 degrees. And well, in that case, the solar day would be longer than it currently is because we'd have to turn even more to face back to the sun. Does that help?
Yes.
Yeah. So that's this part right here that I agree with, that the solar day would be longer. So solar day would be longer. But both, I just don't see it because the sidereal day, like I said, independent, not coupled to orbital rate by definition. I guess the one thing I'd have to check is the actual hard definition of the sidereal day and see if there's something I'm missing about it. But I don't think so. And then discard these. Okay, I'm gonna quickly stop the recording. Go ahead, Teresa.